Nerd Night number 61, MRI Magic, Proton Power, and Why We Play Video Games.
Hi everyone, I am here. I'm here from the physics department at the University of Michigan, here to give a talk about the structure of the proton. So you're not meant to understand the slide yet. We'll get there. This is just sort of an overarching goal. This is basically what my research is. I could just put it up and then just walk away, but I've been told that that's not how you give talks. So we're gonna start with what even is the proton? So we're gonna zoom out a little bit. This is your basic cartoon of an atom. It's pretty popular. It's on my t-shirt. It's not entirely accurate, not just because I spent 10 minutes making this in PowerPoint, but if we were to take this atom and we were to expand it to the size of the wonderful Michigan Stadium, all of the electrons in the cloud outside would be the size of the stands, and this tightly bound nucleus on the inside would be about the size of a flea. There's these really weird length scales that are going on inside atoms. If we decide to zoom in a little bit, what is actually holding this nucleus together in such a bound state is what we call the strong force, or the strong nuclear force. It's a very strong force, stronger than the weak nuclear force, in fact. It holds these protons and neutrons together in this nucleus, and it's what we call a fundamental force. And fundamental is one of those fancy words that physicists really like to use. What it basically means is that it works on pretty much everything, and we don't really understand how it works, but we're working on it. So if we zoom in further into the proton, which is what my research focuses on, the proton itself is actually made up of smaller particles. We call these quarks and gluons. Yes, that is the technical words that they are called. My field is great, or very silly, probably both. And this process that holds these quarks and gluons together is responsible for 98% of the mass of the visible universe, which is great if we understood how it worked. So this proton is made up of 3 quarks, 2 ups and a down, and they have what are called color charge. So the electric force has a type of charge, we call it charge. For the strong force, it has 3 different types of charges, which we call colors. They're not physically colored, red, blue, and green. It's supposed to be an analogy to light, where you combine red, blue, and green light, and you get white, color neutral light. Here we have 3 quarks coming together, and they're making this white, color neutral proton. And they're held together by exchanging what are called gluons, which are the little springs. That is a technical diagram that is generally used. It doesn't usually look like a 5-year-old drew it, but PowerPoint is really difficult, and I have very low patience. It turns out, so this is a really nice cartoon, if I do say so myself, but it turns out that if we look at the proton a little bit more, it actually looks a little bit more like this. So we've got our 3 main quarks that are hanging out, but it's surrounded by what we call our sea of gluons. Sea as in thing that you sail across, not sea as in the letter. And they break into what we call quark-antiquark pairs. So antiquark is a form of antimatter. Most things that you've encountered ever are made up of matter. Antimatter is like the mirror universe. It's the Spock with a beard. It's pretty much the same thing. It just has opposite charge. So they're anti-red, anti-green, and anti-blue, which PowerPoint just doesn't project. It's really annoying. So I just went a little crazy with the colors, and it looks pretty if you ask me. So how the hell do I know any of this? I just said a bunch of random words. I could have been saying science fiction. That comes to the collision part of this talk, which I've represented with the very exciting multicolored thing. That's not a technical diagram. You probably won't see that in other talks. I made it myself. So I really wish that we had a better explanation for how we peer inside the proton, but it's such a very small system that basically what we're left with is just smashing it together at as high energy as we possibly can, and it creates this huge amount of debris that we measure. That's what we're stuck with. From the debris, we try to learn about the initial state before the collision happened. A lot of what we know about protons comes from what we call electron-proton collisions. You get your proton, you chuck an electron with it at as high energy as you can, and you measure the angle and the final state energy that it has. You do this a bunch of different times, and you come up with sort of a picture of the internal structure. And this is a length scale. This is a measurement that is sensitive to length scales. What does that mean? Let's draw the analogy to something we're more familiar with, particularly at our wonderful Michigan roads, potholes. So how I experience this pothole is going to depend on how I measure it, what I decide to drive over it with. If I, for example, decide to drive over it with a tank, pothole's not really going to bother me. It'll look like a smooth, beautiful, wonderful road. That would be the equivalent of a very low energy electron-proton collision. This proton just looks like a big blob. I can't see any of the internal structure. And historically, collisions with electrons and protons were at too low of energy until about the 60s, when we were able to discover these quarks and gluons. If I now decide to drive over this pothole with a car, if I'm not paying attention, that could give me a pretty good jolt. I could wake up in the morning to that. This is a slightly higher electron-proton collision. We're starting to see the main three quarks, we're starting to see some of the gluons, we got a little bit of the C. If I now decide to drive over this with a bike, I'm not recommending that you do this, but I will get a really good idea of maybe the size of that pothole. I might feel some of the debris inside. Again, don't do it, just an analogy. But this would be a higher energy electron-proton collision. Now we still got our three main quarks, but the gluons are taking over. We're starting to see this internal structure. There's a bunch of quarks and anti-quarks flying around. So the actual experiment that I work on is located at the Relativistic Heavy Ion Collider, or RHIC to its friends, which is located in lovely Long Island, New York. Into the Spider-Verse. Great movie, not very accurate about collider physics. So this diagram it's a bit complicated, but what's happening at the bottom is there's a bunch of different structures that are accelerating these protons to very, very high speeds, close to the speed of light. And then at the big blue and yellow rings, these protons are traveling in opposite directions such that they collide at very specific points, where we stuck a bunch of detectors in order to measure all of the debris that's coming out of these collisions. Here we are in the ring underground. We're looking at the two different proton rings that are traveling around. These collisions happen very, very often. When RHIC is up and running, they happen about 1 million times a second. So this is a very high data experiment, and we try to record as much as we possibly can. The actual data set that I'm looking at is from 2015. We started taking data in February, and we went to May, and we took data 24/7. There were a bunch of different people that came in, and my final data set came up to about just over 3 billion collisions. These are very messy measurements, and we're trying to collect as much data as possible such that we can try to extract the actual result that we want to look at. This is the actual experiment I work on. It's called PHENIX, or Pioneering High Energy Nuclear Interaction Experiment. This is our logo. We stuck a sun in it to try to convince people that we didn't misspell Phoenix. We did. This is what it looked like back when it was running. Sadly, PHENIX has stopped taking data in 2016, and this is now an empty room. But this is what it looked like when the data was being taken. So you might have noticed that I'm just talking about proton-proton collisions. I don't have an electron. I've got two blobby things that are crashing into each other at high energies, and I'm actually only measuring one particle in this entire collision that we call the eta particle. And then the X is just everything else that I'm not worried about. And you might be wondering, how am I learning anything that's going on? I'm only focusing on one specific thing. Well, we have a trick. We made it. Here's a slide, full circle. We have gone on a journey. So
one of the protons is polarized. It has its spin pointing in a given direction. And spin is one of those nebulous physics concepts that wasn't really named that well. They're not actually spinning. We don't go forward and spin each of the protons. That would be difficult and probably dangerous. What's happening is spin points in a given direction, and we're telling this proton which direction is up. So I got one proton, I told it which direction's up, I'm colliding with another proton, I can now define everything on this side as left, and I can now define everything on this side as right. And from there, I can measure the asymmetry of a given particle, in this case, the eta particle. So I would expect that 50% of my particles would go this way, and 50% of my particles would go that way. That would correspond to a 0 asymmetry. If I had 100% asymmetry, all of my particles would go to the left. That's probably not good to do. And 0 of my particles would go to the right. These asymmetries are expected to be very, very small. If you assume that the proton is just blobby, all of the internal structure that I talked about earlier doesn't come into effect. Fancy theoretical calculations that I'm still working on understanding in the 70s predicted that these asymmetries would be less than 1%. There was supposed to be a formula there. I'm assuming that you had a formula in your mind while I was explaining. I did a great job. You're right. You didn't need the formula. These asymmetries aren't less than 1%. They're huge. They're as big as 40%. I really love showing this plot, not just because my advisor had a hand in making it, and it's like a really low effort way of sucking up, but if way over here on the left side, this was a measurement that was done in the early 90s, back when these collisions were at very low energy, and everyone said, sure, the asymmetries are large, but like, we don't really understand the structure at that point. Like, we're not worried about it. Sure, our theories just aren't going to work at that point. It's fine. Experiments got better. Collisions got high enough energy. Eventually, RHIC turned on way over there on the right. These collisions are at high enough energy. We should understand what's going on. We don't. We have to start thinking about different things that are happening in the proton. Maybe the quarks and gluons are wiggling around, and we have to worry about that. Maybe there's multiple interactions that are happening. So here is kind of a summary slide of what I've been working on for the past 2 years. We've got our PHENIX detector, we've got our polarized proton collision. I'm looking at the eta particle that comes out. You might be able to tell from this diagram, I think I got the perspective right, that this detector only takes up a very small point in space. I'm only able to look at particles that are coming out at like a 90-degree angle. So collision, stuff's coming out at a 90-degree angle. I'm not measuring a large asymmetry. I'm measuring an asymmetry of 0. You could maybe make an argument that there's some kind of trend. It's 0, trust me, it's definitely 0. There have also been measurements done that showed that this asymmetry was larger, as large as 20%. And you might be worried at this point, I'm contradicting an earlier measurement. That's bad. It's okay, don't worry about it. We're looking at different particles at different angles. So I'm looking at particles that are, we've got our polarized proton, we've got our unpolarized proton, they're colliding. I'm looking at particles that are at a 90-degree angle. These larger asymmetries are measuring particles that are closer. They're at forward, they're closer to what we call the beamline. And so the asymmetry has a different value depending on where you measure it in space. So science is still being done. What I'm doing is still useful. At least that's what I tell myself to get myself out of bed. And if you look at this plot, this is the older PHENIX measurement that was done also with particles coming out 90 degrees. They also measured 0 as the black points. I'm the red points. I measured 0 a lot better than they did. Science has been done. So to conclude, the strong force is mysterious. We're still working on understanding how it keeps the proton together. And I also wanted to take an opportunity to thank the RELATE program, which is a wonderful program at the University of Michigan that takes in sad grad students like myself that don't know how to speak about their research and teaches us how to talk like human beings. So without this talk would have been a lot less coherent. So thank you.
This program was recorded on January 17th, 2019 at Live, 102 South 1st Street, Ann Arbor, Michigan.